Alright, hi there, this is Prashant, and in this series, we'll be having a look at a number of sorting algorithms in data structures, and we'll try to visualize each and every sorting algorithm, and so that we do not end up confusing between one sorting algorithm and another sorting algorithm. So let's just begin with insertion sort straight away. For understanding insertion sort, I want you to visualize this algorithm as picking a key and inserting it into the right position, that is the right lock. So we just pick a key, and of course one key goes into one lock. So we'll have to actually just try finding the right position for the key, and once we do so, we insert it right away. So that is you can say a gist. That is how this algorithm works. So let us just look at the pseudocode here. We just start with 1, I is equal to 1 and not I is equal to 0, and we just go all the way to till n minus 1. So we basically we just assume the first element to be sorted already. That's why we begin with index 1. And this may seem overwhelming at first, but this is very simple to understand if we can visualize this process. So in this, we've been given an example to sort 5, 4, 1, 2, 3 in ascending order. Let's see how it goes. In the first iteration, I is equal to 1 here. So have a look at the pseudocode. We start I variable from 1 to n minus 1, and we have the second loop inside the for loop. So we have two loops here. The first element, we just pick each element and we assume it to be the key, and then we just compare each key element with the previous element, and if this key element is actually less than the previous elements, we try moving the elements by one place, and we keep doing so until we have found the right position for us to insert the key element. So that's how this thing works. We keep doing so until we find the right position, and then once you've found the right position, we insert it right there. So let us just start with the insertion sort algorithm. I is equal to 1, the first iteration. Key is going to be 4 because we assume 5 to already be sorted. So we now compare this key with the previous element. So j is equal to I minus 1, in this case a of 0. So a of 0 is 4 here. We compare it, key is 4, a of 0 is going to be 5. So we compare 4 with 5. 4 is less than 5, so we move 5 by one position, and we have this right there. And once you found the right position here, we've hit the end of the loop, that is j greater than or equal to 0. So we insert the key in the right position, and we've completed the first iteration. Now let us just move on to the second iteration. Key is equal to 1 here, and we compare key with 5. 1 is less than 5, so we move 5 by one position. And now 1 is again less than 4, so we move 4 by one position, and that's it. We've reached the end of the loop. We've found the right position, a of j plus 1, that is, and we've inserted 1 at the required position. We repeat the same thing for the third iteration, I is equal to 3. In this case, key is going to be 2. So what I want you to understand is anything to the left of key is already sorted, and whatever is to the right of key are the elements that need to be sorted. So we just keep comparing it with the previous element, and then we keep moving it one by one till we find the right position, and then we insert it there. Now we repeat the same thing. Key is equal to 2 in this case. Is 2 less than 5? Of course it is. So we move 5 by one position, and then is key 2 less than 4? Yes it is. So we move 4 by one position. And is key less than 1? No, it is not. So we stop right there, and then we come out of the loop. A of j plus 1 is equal to key. In this case, a of 1 is equal to key. So we found the right position, and we've inserted 2. Next iteration, the last iteration, I is equal to 4. So key is equal to 3 here, and now this actually starts with the previous element. In this case 5. Is 3 less than 5? Yes it is. So we just swap, we move 5 by one position, And then is 3 less than 4? Yes, it is. We move 4 again ahead by 1 position. And now is 3 less than 2? No, it is not. 3 is greater than 2. So we stop right there. Then we insert the key at the right position. That is 3 at the right position. And there you go. We've reached the end of the loop. And our sorting algorithm is complete. And all the elements 1, 2, 3, 4, 5 are sorted. Now let us try implementing this code and see if it works. Alright, here I've just converted my pseudocode into a working C++ program. The code is pretty self-explanatory if you've actually understood how the sorting algorithm works. Uh, there we go, I've just taken the array size and then taken the elements one by one, and then this is my sorting algorithm. I run the I variable from 1 to n minus 1, then taking the I just create my key variable j is equal to I minus 1, and then I compare my key variable with the previous elements one by one until I find the right position. I keep moving them, and once I found the right position, I insert my key, and that's it. The algorithm is complete. Let's see if my algorithm works. Enter the array size 5. My elements are going to be 5, 4, 1, 2, 3, and there you go. The elements sorted in ascending order are 1, 2, 3, 4, 5. If you want them in descending order, it's fairly simple. Just reverse the indexes here. Run it from n minus 1 to 0, I is equal to 0, and then try printing fi. This is just going to work fine. That's it. So that's how insertion sort algorithm works. The key takeaways from this video are: this is pretty obvious. It's a sorting algorithm to sort the elements in ascending or descending order, as the name implies. And I wanted you to visualize this algorithm as just inserting a key, picking the key, and then finding the right lock for it, and then inserting it right there. Something like this. And anything to the left of key is sorted, and anything to the right of the key is unsorted. So as the algorithm proceeds, the whole array is going to be sorted. Now the time complexity part for this is going to be O of n square, big O of n square. That is because we have a loop inside a loop. So two loops, n into n, that's going to be O of n square, big O of n square. The time complexity in the best case is going to be omega of n. That is because if the best case is going to be that case where the given elements are already going to be sorted. If the given elements are already going to be sorted, this part of the loop doesn't work. I mean, it doesn't enter the loop. So we just have n steps here because the key element is not going to be less than the previous element since the list is already sorted. The array is already sorted. So this loop doesn't execute at all. We just have n steps to cover, and that is why our time complexity in best case is omega of n. Thank you, and that pretty much is it. Peace.